Hey guys, welcome to Unit 8, Notes C2, the second half of our notes on weak acids and bases. Now we want to look at a new version of formulas, looking at the Ka and Kb in the same context that we could for the hydrogen or hydroxide ion concentration. Remember that the P in pH basically explains the power or the factor of 10-fold multiplication. As you increase one thing, the other thing increases 10-fold. So we have these same expressions that we've used to connect pH to H plus or POH to OH minus. We can apply them in the same way to connect pKa to the negative log of Ka or pKb to the negative log of Kb. And from there we can also derive that Ka would be the antilog of the negative pKa, and that Kb would be the antilog of the negative pKb, just like the hydrogen concentration would be the antilog of the negative pH. So same exact mathematical relationships. Just like pH and pOH, these numbers for pKa and pKb are usually positive, and there's no units involved, it's simply a scale. The relationship between Ka and pKa is going to be inverse, as well as with Kb and pKb, just like how pH and the concentration of H is also inversely related. The more hydrogen ions you have, the more acidic, which goes with a lower pH. So we have the same exact inverse relationship between the Ka and pKa versus Kb and pKb. P still represents a power or a 10-fold change in the value of the Ka, and the K expressions are still temperature dependent, just as they have always been. Next, I want to derive an equation that connects Ka, Kb, and Kw. So starting with Ka, if I look at an acid dissociation to produce the hydrogen ions and the acid or anion ions, yes, we are having some water in order to accept the hydrogen, and that would then form hydronium. But as we talked about before, not a super important detail because these are the same and the water is not in the expression. So our Ka, or equilibrium expression for this acid dissociation, is simply H plus times the anion over the original acid, leaving out the water. Now I want to look at the dissociation of a weak base, and I know these symbols look different than what we used before, but I'm trying to use similar symbols for both the acid and base dissociation so we can see what would actually cancel. So if we look at this in terms of conjugate acid and conjugate base, our hydrogen is actually going from the water over to the base, which would be the anion here, and so we can get the conjugate acid being formed and the conjugate base being our hydroxide. And so if we take the water out of that equilibrium expression, we get Kb to be equal to this constant. Now if I try to multiply Ka times Kb, I can then kind of substitute in these two expressions. So with Ka times Kb, when we plug in what Ka and Kb are equal to, we can cancel a couple things out, including the original acid and the original anion. And so we just are left with hydrogen concentration times hydroxide concentration, which coincidentally is also equal to Kw. Therefore, Ka times Kb is equal to Kw. If Ka times Kb is Kw, then if we do the negative log of both sides, we can get pKa plus pKb equals pKw. Keep in mind your logarithm rules, that's now a plus sign. And we know what the Kw is, so we know what the pKw is, just 14. So now we know that the pKa plus the pKb equals 14. Pretty useful formula right here. We're also going to see an inverse nature in the relationship of acid to base. Just like when the pH is high, the pOH is low, or vice versa. When the Ka is high, the Kb is low, and vice versa. So what this actually means in practice is that a strong acid will have a very weak conjugate base, or a strong base would have a very weak conjugate acid. So here is an example of our complementary nature between the strength of the acid and the weakness of a base. So sulfuric acid, H2SO4, one of the 6 strong acids with 100% dissociation. If I look at its conjugate base, in other words, I've removed an H+, H2 becomes just H1, and the neutral now is negative because we've lost the positive. So HSO4- would be its conjugate base. That super strong acid would produce a super weak conjugate base. And of course the opposite is true as well. A weak acid would have a very strong conjugate base. Complementary in nature. Alright guys, that does it for Unit 8, Note C. Our next set of notes on Notes D will look at hydrolysis. I'll see you there.